Lay your hand flat on a window on a cold morning, one that has fogged over evenly, the whole pane gone soft and grey, and the same to the touch everywhere you press. Now imagine that under your palm, in one spot, the glass is colder than everywhere else. Not a little colder, stubbornly, wrongly colder, in a way that shouldn't be possible if the whole window fogged the same way at the same time. You lift your hand, you press again, and it's still there. One patch that refuses to match. There is a spot like that on the sky, not on a window, on the oldest light there is, the faint glow left over from the young universe, a glow famous for being almost perfectly smooth in every direction you point. Almost. Because in one direction, down in the southern sky toward a dim constellation called Eridanus, the map goes cold. A patch bigger than you would think the universe could make by accident, and colder than the smooth story wants to allow. And here is the part that pulls you in. A man who later won a share of the Nobel Prize in Physics looked at marks in that same ancient light and said they might be bruises left by a universe that existed before ours. Most of his field does not agree with him. The plainer suspects don't quite add up either. So what made that one patch of sky so cold? The oldest light in the universe is called the cosmic microwave background. And for most of this, you can picture it as a photograph. The first photograph ever taken of everything from the inside. Here is what that photograph shows. Go back to when the universe was very young, only a few 100,000 years old. It was hot, it was dense, and it was filled with a glowing fog, a plasma of bare particles so thick that light could not travel in a straight line through it. Light bounced, scattered, got absorbed and spat back out, the way your car headlights get swallowed in thick fog and you can't see the road. The whole universe was that fog, everywhere, glowing. Then the universe expanded and cooled, the way anything cools when it spreads out, and at a certain moment, roughly 380,000 years after the beginning, it cooled enough for that fog to clear. The bare particles settled into whole atoms, the haze lifted, and for the first time light could fly. It has been flying ever since. And some of that light, released in that one clearing moment, is arriving at our instruments right now, after a journey of nearly the entire age of the cosmos. That is the cosmic microwave background. It is the flash of the fog lifting, still reaching us, from every direction at once. Think about that for a second, because it's easy to say and hard to feel. When you look at this light, you are not looking at a thing in space. You are looking at a time. You are seeing the moment the universe went transparent, spread out across the whole sky like the inner wall of an enormous sphere with us in the middle. There is no older light. Past it, further back, the fog is still there and always will be, from our point of view. This is the wall, the last thing we can ever see by ordinary light. Now, when that fog cleared, it was hot, around 3,000 degrees. So why do we call this the microwave background, a cold thing, a thing measured in microwaves? Because the universe has kept expanding for all those billions of years since, and the expansion stretches the light along with it, dragging those once fierce, hot wavelengths out longer and longer until they've slid all the way down into the microwave band, the same family of waves your kitchen oven uses. Stretched and cooled, that 3,000-degree glow now sits at a whisper above the coldest temperature there is, about 2.7 degrees above absolute zero. The fire of the young universe, cooled by distance and time into the faintest possible chill. And here is the fact I want you to hold on to, because everything hangs on it. That glow is smooth. Astonishingly, almost unbelievably smooth. If you measure its temperature in one direction and then in another and another, all across the sky, the number barely changes. The variation from the smoothest spot to the roughest is only about 18 millionths of a degree. Not 18 degrees, not 18 tenths of a degree, 18 millionths. Picture a calm bath drawn to exactly the temperature you like, and now imagine that across the whole surface of that bath, from one end to the other, the temperature never varies by more than a rounding error you could never feel with your skin in 1,000 years. That is how even this ancient light is. The whole visible universe warmed to the same faint temperature to within a hair. That smoothness is not a small thing. It is one of the great confirmations of the standard picture of cosmology, the model physicists call ΛCDM, which describes a universe that began hot and dense, expanded and cooled, and which should look more or less the same in every direction. The smoothness is the standard model being right, spectacularly right, across the entire sky. So this is where the puzzle sharpens. When something is that smooth, that evenly warmed, you don't expect to find a flaw in it. You certainly don't expect to find a flaw the size of the one that turned up. Because the smoothness, it turns out, is not perfect, and the imperfection is the whole story. The first person to notice was working in northern Spain, in the city of Santander, at an Institute of Physics in the year 2004. A researcher named Patricio Vielva, working alongside Marcos Cruz, Enrique Martinez Gonzalez and their colleagues, was going through the sky map that NASA's WMAP satellite had produced. WMAP had launched in 2001 with a single job: to measure that ancient light more precisely than anyone ever had, to take the smoothest possible portrait of the young universe. And it did. The map was beautiful, and it was even, millionths of a degree of wobble from place to place, exactly as the smooth story promised. But the Santander team weren't only admiring it. They were running it through a mathematical filter, a tool with a wonderfully odd name, the Spherical Mexican Hat Wavelet. Don't let the name intimidate you. Think of it as a specially shaped magnifying glass. You slide it across the map and it's built to light up whenever it passes over a feature of a particular size, a bump or a dip that stands out from its surroundings on a certain scale. A metal detector doesn't tell you what a coin looks like, it beeps louder where there's more metal. This filter beeped. What it detected was something that shouldn't have been there. In a truly smooth, random universe, the little temperature wobbles in the map should follow a very particular kind of statistics, the calm bell curve randomness that comes out of the simplest theories of the young cosmos. Physicists call that Gaussian, and this map was Gaussian, everywhere. Except that the filter found an excess, a lump in the statistics at a scale of a few degrees on the sky that plain randomness struggles to produce. Here is the human detail I find genuinely striking, and it's the thing that told them this was real and not just noise. When they hunted down where the odd statistics were coming from, it all traced back to a single location. One patch. And when they mathematically removed that one patch from the map and looked at everything else, the rest of the sky went right back to being perfectly, boringly Gaussian. The entire anomaly, the whole strange signal, lived in one place. Cover that one spot with your thumb and the universe behaves. Uncover it and it misbehaves. The following year they pinned it down precisely to a location in the southern sky in the direction of Eridanus, the river constellation. And they ran the obvious test. They generated simulated skies, thousands of them, universes that were purely smooth and random the way the standard picture says they should be, and they asked a simple question. In how many of these fake but honest universes does a cold patch this big and this deep just happen to appear by chance? The answer that came back was small, somewhere under 1%. Depending on exactly how you measured it, as few as 2 in 1,000 of the random skies produced anything like it. So how cold is this spot, really? On average, it runs about 70 millionths of a degree below the surrounding sky, and at its coldest points, it dips to around 140 or 150 millionths below. Now hold that against the number I asked you to remember. The whole sky varies by about 18 millionths of a degree. This one spot is colder than that, several times over. It is, in the most literal sense, off the chart the rest of the map is drawn on. And it is enormous. It spans about 10 degrees across the sky, roughly 20 full moons laid side by side. Translated into real distance across the face of that ancient wall of light, the cold region stretches more than 1 billion light-years wide. Let that scale settle, because it's the strange part. This is not a small blemish. This is a cold region larger than the biggest structures we know how to build a universe out of. On the smoothest surface that exists, a surface even to millionths of a degree, sits a single cold mark over 1 billion light-years across. And there's a twist in the shape of it that took a few more years for people to fully appreciate, and it changes what we're even looking for. The cold spot is not just a cold blob. Around the cold center there is a faint, warm ring, a raised rim of very slightly hotter sky encircling the chill, stretching out to about 15 degrees. Cold heart, warm halo. It's this specific profile, the cold middle wrapped in a hot ring, that turns out to be the real signature, the thing any explanation has to reproduce. It's easy to imagine a process that just makes a patch colder. It's a lot harder to imagine one that makes a patch colder and rings it with a matching band of warmth. Keep that ring in your mind. It quietly rules things out, later on, that would otherwise walk free. Now, the first honest question anyone asks is the skeptic's question, and it's a good one. Cameras have flaws, instruments have quirks, a cold telescope, a bad detector, a smear of dust in our own galaxy sitting in the foreground. Any of these could paint a fake cold patch on the map that has nothing to do with the young universe at all. Maybe the cold spot is just a smudge on the lens. That question got answered, and answered thoroughly, by a second satellite. In May of 2009, the European Space Agency launched a spacecraft called Planck, and Planck was, frankly, a better instrument than anything before it. It carried 74 detectors watching the sky across 9 different bands of microwave color, some of its parts chilled to within 1/10 of a degree of absolute zero to keep their own warmth from polluting the measurement. It swept the entire sky twice a year for over 4 years, seeing detail down to a fineness of about 5 arc minutes, a fraction of the width of the full moon. It was designed to catch exactly the kind of contamination a skeptic worries about, because it could see the sky in multiple colors at once, and real dust in our galaxy glows differently in different colors than ancient light from the young universe does. If the cold spot were a foreground smudge, Planck would have caught it changing color and thrown it out. It didn't. Planck looked in the early 2010s and confirmed the cold spot as a genuine feature of the ancient light itself. Not dust, not a detector glitch, not a WMAP quirk, because here it was again in a completely different instrument built by a different agency with different flaws. The spot is real. It is out there, printed into the oldest light in the universe, and it has been sitting there since 380,000 years after the beginning, older than the first star. So we're left with the puzzle in its full form, and it's a beautiful one. The universe's smoothest object, its very first photograph, is smoothed to millionths of a degree, exactly as the standard picture promises, except for one real, confirmed, billion light-year cold patch wrapped in a warm ring, sitting in the southern sky, colder than the smooth story is comfortable with, appearing in fewer than 1 in 100 honest random universes. It's really there. Something really made it. So the question that drives everything from here is simple to ask and, it turns out, punishingly hard to answer. If everything else is so smooth, what made that one spot so cold? The most natural answer, the one that had physicists nodding when it was first proposed around 2006, doesn't require any new physics at all. It doesn't need other universes or exotic events. It needs empty space. A lot of empty space. Here's the idea, and it starts with a picture. Imagine the ancient light setting out from the wall of the young universe, flying toward us across billions of years. It doesn't fly through nothing. It flies through the universe we actually have, which is lumpy on the largest scales, clustered into a great cosmic web of galaxies and clusters strung along filaments, with vast, quiet, near-empty regions in between. Those enormous empty regions have a name: supervoids, bubbles of below-average emptiness, hundreds of millions of light-years across, where there's simply less matter than usual. Now, what happens to a beam of ancient light when it passes through one of these giant empty regions? This is where you meet the mechanism that carries this whole explanation, and it has a name we'll get to. But let me give you the picture first, because the picture is everything. Think of a ball rolling across a landscape toward you. When it reaches a valley, it rolls down into the dip, picking up speed, and then it has to climb up the far side, giving that speed back. In a fair world, it arrives at the top of the far slope with exactly the energy it had coming in. Down and up, borrowed and repaid, no net change. Light behaves like that ball when it crosses a region of gravity. Falling into a dense clump, it gains a little energy. Climbing back out, it gives that energy back. Even trade. But now imagine that while the ball is down in the valley itself is slowly stretching, getting wider and shallower underneath it. The ball rolled down a steep slope, but by the time it climbs out, the far slope has flattened. It doesn't have to climb as high as it fell. It comes out the other side having given back less energy than it gained. It emerges a little richer, or in the case of an empty region, a little poorer. That's the trick. Our universe isn't only expanding, the expansion is speeding up, driven by whatever we call dark energy. And that acceleration stretches these giant landscapes while the light is still crossing them. When ancient light falls into a supervoid, an underdense region, it's really the opposite of a valley, more like a gentle hill of below-average gravity. And while the light is inside, dark energy stretches that hill flatter. The light climbs out, having lost a touch of energy it never got back. And light that has lost energy is cooler light, a colder patch on the map. This mechanism has a name, two names really, from the physicists who worked it out. Broadly, it's called the Integrated Sachs Wolfe effect, and its nonlinear cousin, for structures that are actively evolving, is the Rees Sciama effect. But you don't need to memorize those. You need the ball and the stretching valley. A vast emptiness in front of the cold spot, cooling the light that crosses it. Clean, elegant, requires nothing new. Everyone wanted it to be true. So the obvious next question is the one that turns a nice idea into science. Is the emptiness actually there? Don't just tell me a void could do it, show me the void. And they did. In 2015, a team led by Istvan Sapudi, using infrared and optical surveys, found it. A genuine supervoid, sitting right in the direction of the cold spot, in Eridanus. Not a small one. It's about 1.8 billion light-years across, one of the largest underdense regions ever mapped, with something like 20% less matter than average. Its center roughly 2 billion light-years from us. It was later confirmed and studied in detail by a team led by Andras Kovac using the Dark Energy Survey, a project running on the 4-meter Blanco telescope perched on Cerro Tololo in the Chilean Andes. They mapped the region not by counting galaxies, which is unreliable, but by weighing the actual mass in front of the spot through the way its gravity bends the light of galaxies behind it. And the void was real. In fact, in the entire Dark Energy Survey dataset, it stood out as the single most prominent emptiness of its kind. So the suspect exists. There really is an enormous void sitting right where the theory wants one. Case closed, surely. Here is where the story turns, and it's my favorite kind of turn, because it's the moment the obvious answer, the one everyone wanted, quietly fails. And fails in an honest way that only careful measurement could reveal. The void is real. and it is nowhere near big enough. When Kovacs and his colleagues did the arithmetic, using the standard model of the universe to work out how much cooling this confirmed void should produce through that ball and stretching valley effect, they got a number, and the number was small. Their conclusion, published in 2022, was that the void can only explain about 10 to 20% of the temperature drop we actually see. The expected chill from a void like this comes out to around 20 millionths of a degree. The chill we measure is around 150 at the center. The suspect can account for a fifth of the crime at best. The other 80% has no explanation from the void at all. And an independent test made it starker still. A group led by Rory Mackenzie in 2017 looked carefully along the exact line of sight to the cold spot and found not one clean void, but a string of 3 separate underdense regions at different distances, interspersed with ordinary clumps. Adding up the cooling from all 3 stacked together, they got about 9 millionths of a degree, against the 70 we need to explain. The line of sight, examined honestly, delivers a rounding error where we needed the whole answer. There's a quieter detail from that same work that I keep turning over, because it's the kind of thing that should make you cautious. They looked at a control field, an ordinary, unremarkable patch of sky picked essentially at random, and they measured the voids sitting in it. That control patch contained voids of similar size to the Eridanus supervoid, and yet there was no cold spot in front of it. If big voids reliably made cold spots, the sky should be freckled with them wherever the big voids are. It isn't. The suspect not only has a weak motive, it has an alibi. Voids this size sit in front of ordinary, unremarkable sky all the time and leave no mark. Now, science being what it is, that wasn't the final word, because there was a loophole and honest people kept it open. What if the effect of voids on ancient light is simply stronger than the standard model predicts? There were tantalizing hints of exactly that. Other studies of large voids elsewhere that seem to show a cooling imprint several times stronger than the model said it should be, 5 times stronger, with real uncertainty on that number. If voids punch above their weight for reasons we don't yet understand, maybe the Eridanus supervoid could still be the answer after all. The door stayed open. But it needed a much better test than counting galaxies, because counting galaxies is treacherous, thrown off by dust and by the fact that surveys always miss the faintest objects. The better test was gravity itself. And this is where the void explanation met its hardest challenge, in 2022, from a team led by a physicist named Owusu working with Planck's data. Their tool was gravitational lensing. The idea is lovely in its directness. Mass bends light. So whatever mass sits in front of the cold spot, void or clump, will subtly distort the ancient light passing around and through it. And by measuring that distortion, you can weigh the intervening universe directly, without counting a single galaxy, without worrying about dust. You read the mass off the bending of light, the way you might feel the weight of something by the way it dimples a stretched sheet. They read the mass, and the verdict was decisive. The lensing showed there simply is not enough of a mass shortfall along that line of sight to have cooled the light the way the void story needs. The numbers are worth hearing because they show a mind changing under evidence, which is the whole point of the enterprise. Using the temperature map alone, the odds had favoured a void explanation, something like 56-1 in favour. Then they folded in the lensing, the direct weighing of the mass, and the odds flipped hard, to roughly 13-1, or by another map, 20-1, against a large void being the cause. The same evidence that could have confirmed the void instead ruled it out. A sufficient void in front of the cold spot, the kind that could do the whole job, would have left a lensing fingerprint. It didn't leave one. It isn't there. So step back and feel where we are, because it's a genuinely strange place to stand. The most reasonable, most conservative, new physics-free explanation for the cold spot, the one that requires only an ordinary big empty region and a well-understood effect, has a real suspect. And the suspect has been weighed directly by the bending of light and comes up far too light to have done it. The void is real, and it is innocent of most of the crime, which throws the question wide open again and invites answers that are a great deal stranger than empty space. Before we get to the strangest of them, there's a candidate that lived a brief, respectable life and deserves its moment, because for a while it was the most convincing idea anyone had. It came from a heavyweight team in 2007, published in the journal Science, and among the authors was Neil Turok. Their proposal was something called a cosmic texture. Here's the picture, and it needs one new idea introduced gently. In the extremely early universe, hotter and denser than the fog we've been talking about, physicists think the fundamental fields that fill space may have gone through phase changes, a bit like water freezing into ice. And when things freeze, they don't always freeze uniformly. Ice on a pond forms in patches that meet at seams and knots and mismatches, places where the crystal was pointing one way over here and another way over there, and the two domains had to reconcile at a boundary. In the early universe, an analogous freezing of a field could leave behind knots, localized snarls in the fabric of space called topological defects. A texture is one kind of such knot, and as it collapses and unwinds, its concentrated energy warps the space around it, and that warp could imprint a cold spot, of about the right size, onto the ancient light passing by. For a while, the texture idea fit rather well. The statistics mildly favored it, and it naturally produced a feature of roughly the right scale, in roughly the expected numbers across the sky. It was, for a couple of years, the front-runner among the exotic explanations. But it faded, honestly and undramatically, the way most ideas fade, not because someone disproved it with a flourish, but because better analyses stopped finding any preference for it. More careful statistical work found no real evidence favoring a texture over plain chance, and when the lensing came in, there was no gravitational trace of the kind of concentrated warp a collapsing texture would leave. It's still on the list, it's just no longer leading it. Which brings us at last to the idea in the title, and to a man worth introducing carefully, because his story is where boldness and caution in science stand right next to each other. Roger Penrose was born in England in 1931, a mathematical physicist of the very first rank, the kind of person whose name is attached to theorems still taught decades later. In 1965, as a young man, he proved something profound about Einstein's theory of gravity, that, under general conditions, when enough matter collapses, the formation of a point of infinite density, a singularity at the heart of a black hole, is not some fragile mathematical accident, but a robust, almost unavoidable consequence of the theory. That result reshaped how physicists understood black holes, and more than half a century later, in October of 2020, it earned him a share of the Nobel Prize in Physics. He won for the singularity work. Hold that clearly, because it matters for reading the title honestly. The Nobel was for black holes. It was not for the idea we're about to discuss, an idea most of his colleagues do not accept. Because Penrose, around 2005, proposed something far more radical, a picture of the cosmos so bold it's hard to hold in your head the first time. He calls it conformal cyclic cosmology, and its central claim is this: what we call the beginning may not have been the beginning. There may have been a universe before ours, and it may have left marks we can see. Let me build this one slowly, because it's beautiful even if it turns out to be wrong, and because it's easy to garble. Penrose asks you to think about the very far future of a universe like ours. Keep expanding, keep accelerating, for spans of time so vast the current age of the cosmos is a rounding error against them. All the stars burn out, matter falls into black holes. The black holes themselves, given almost unimaginable stretches of time, slowly evaporate away, radiating themselves into nothing but the faintest possible light. In the end, you're left with an enormous, empty, cold universe filled with nothing but radiation drifting forever. Now here's the move that makes it cyclic, and it's a mathematical one that I'll translate. Penrose argues that in that far future, once essentially everything has decayed into pure radiation, the universe loses track of scale. Radiation, unlike matter, doesn't carry a built-in sense of size or of clocks. And Penrose's claim is that a universe with no rulers and no clocks left in it, infinitely large and old, becomes mathematically indistinguishable from something infinitely small and young. A fresh, hot, dense start. Picture a subway map. It keeps every station, every junction, every angle at which the lines cross, but it throws away the true distances entirely. On the map, a 2-minute walk and a 2-hour ride can look the same length, because the map only preserves the connections and the angles, not the scale. Penrose's mathematics does something like that to the far future of the cosmos. It's called a conformal rescaling, and conformal is just the technical word for a map that keeps angles but discards absolute size. Apply that rescaling, and the cold, empty, infinite end of one universe maps smoothly onto the hot, dense start of the next. The end becomes a new beginning. He calls each full cycle, from hot, dense start to cold, infinite end, an eon. And in his picture, ours is not the first. There were eons before us, and the marks of the last one could, faintly, be printed on our sky. What marks? This is the striking, testable part, the reason this isn't pure philosophy. In the previous eon, there would have been supermassive black holes, some of them merging, some of them slowly evaporating over those enormous stretches of time. And Penrose argues that the energy from those evaporating giants, released across the crossover from one eon to the next, would show up in our ancient light as faint, roughly circular warm patches, low-variance rings with a particular structure. He and his collaborators gave them a name that borrows from the physicist who first described how black holes evaporate. They called them Hawking points. So now you have a genuine prediction. If the previous eon picture is right, our sky should carry concentric circular features, faint rings, at particular angular sizes, marking where the dead black holes of a vanished universe poured out their final energy. Warm bruises in the oldest light left by a cosmos that ended before ours began. It's an astonishing thing to go looking for, and they went looking. In November of 2010, Penrose, working with Vahe Gurzadyan of the Yerevan Physics Institute in Armenia, announced that they had found them. Families of concentric circles in the WMAP data where the temperature varied unusually little, and they claimed the significance was very high. The news travelled fast, because of course it did. Fingerprints of a universe before ours in the actual data. Here's where you get to watch science do the thing it does best and fastest, which is check. Within weeks, not months, 3 separate teams working independently repeated the analysis. And here's the careful, honest result, the one that's easy to get wrong if you're rooting for a side. They found the circles. The circles were really in the data. Ingun Vehus and Hans Christian Eriksson put it plainly, that they did reproduce the claimed ring structures observed in the WMAP data. So the rings weren't fabricated, that's not the problem. The problem is what the rings mean, and to see it you need one more idea, an idea that quietly haunts this entire subject. When you look for something in static, you will find it. Think of listening to radio static, that hiss between stations, and becoming convinced you can hear a faint tune in it. If you listen long enough, in enough of the hiss, you will always hear something, because random noise, given enough chances, throws up patterns that look meaningful. The test is not whether you can find a pattern. The test is whether the pattern appears more often in the real data than it would in pure noise. That's exactly what the 3 teams checked. They generated simulated skies, ordinary random universes with no previous eons, no Hawking points, nothing but standard physics, and they looked for concentric, low-variance circles in those. And they found them just as often at just the same strength as in the real sky. Weihus and Ericsson said it directly, that their simulation results did not agree with what Gurzadian and Penrose had presented. The claimed high significance, it turned out, rested on comparing the data against the wrong kind of expectation, effectively assuming the sky should be pure, featureless noise, when the real sky, even a perfectly ordinary one, is naturally full of exactly these kinds of faint, circular coincidences. The rings were real. The rings were also just what an ordinary universe produces. There was nothing left over to explain with a previous eon. The physicist Sean Carroll relayed the rebuttal on his blog the very day two of the papers appeared, and the exchange became a small, clarifying lesson in how the field handles a bold claim from even its most celebrated members. Respectfully, and by checking, and by declining to follow when the check comes up empty. Penrose didn't abandon the idea, and years later, in 2018 and 2020, he came back with a stronger version, working with Christoph Meissner, Pavel Narovsky, and Daniel Ahn, this time using Planck's better data and a more specific search for the Hawking point signal. They claimed a very high confidence again, something like 99.98%, and once again, the check came. In 2020, Dylan Zhao and Douglas Scott reanalyzed the same signal carefully, paying attention to how you count the chances you gave yourself to find something, and the confidence collapsed. Where the original claim was 99.98%, their reanalysis found the excess sat at only about 87%. And 87% sounds high until you learn that in this business it's barely more than one standard deviation, which is to say, barely anything at all, the kind of blip you'd expect to see wander in and out of noise all the time. Their conclusion was blunt. There is no statistically significant evidence for the presence of Hawking points in the ancient light. A machine learning study a few years later, sifting the same maps with different methods, came to the same quiet null. So where does that leave Penrose's picture? Not disproven exactly. You can't easily disprove a claim about a universe before ours, but unsupported. The specific, testable fingerprint it predicted has not survived independent scrutiny. The field, respectfully, does not follow him here. And I think there's something worth sitting with in that, which is that both halves of this are science working correctly. A brilliant mind proposing something audacious and testable, and a community of others insisting, without malice, on checking it against ordinary chance before believing it. The boldness and the caution are not opponents, they're partners. Now, I want to be careful about the title's exact words, because the honest version is more interesting than the loose one. Penrose's picture is not strictly another universe hitting ours. It's a universe before ours, a prior eon, feeding into the start of this one. A different exotic idea, a genuinely separate one, is the picture where another universe strikes ours sideways, and that idea comes from a completely different place. It's worth telling because it's the only one of these where somebody actually built the tool to go hunting for a collision and pointed it at the whole sky. The idea is called eternal inflation, and it's multiverse. Here's the gentle version. In the standard account, the very early universe went through a burst of staggeringly fast expansion called inflation, a fraction of a second in which space ballooned enormously. Some versions of the theory suggest that inflation, once started, never fully stops everywhere at once. It keeps going in the wider backdrop, and every so often a region settles down and stops inflating, forming a bubble, a pocket universe, that then grows and cools into something like the cosmos we know. If that's right, our entire observable universe, everything we can see in every direction, is the inside of a single such bubble, one among an unimaginable number of others, all of them separate pockets in an endlessly inflating sea. And here's the part that turns philosophy into a measurement. If our bubble formed near other bubbles, then early on, before inflation stretched everything apart, our bubble could have brushed against a neighbor, collided. And a collision like that would leave a very specific mark because of its geometry. A neighboring bubble, being roughly spherical, would strike our own along a circle, and the imprint it left on our ancient light would be a circular disk, perfectly symmetric around its center, either warmer or cooler than its surroundings. A literal round bruise on the sky, the scar of a sideways encounter with another universe. The person who decided to go looking was a graduate student. In 2011, at University College London, Stephen Feeney, working with Haranya Peiris, built an algorithm to hunt through the WMAP data for exactly these symmetric circular disks, at any size, anywhere on the sky. Peiris described what drew her in, and I love how plainly she put it, that it's a very hard statistical and computational problem to search for all possible radii of the collision imprints at any possible place in the sky. But that's what pricked her curiosity. Feeney called it what it was, an opportunity to test a theory that is genuinely staggering, that we exist within a vast multiverse. Think about what that sentence means as a piece of work. Someone wrote a computer program to search the oldest light in the universe for the dents left by collisions with other universes. Whatever you think the answer would be, the fact that this is a thing a person can do, rigorously, with real data, is one of the quietly astonishing facts about the era we live in. And the answer? They found some candidate features, a handful of roughly circular shapes worth a second look, but nothing that rose above what you'd expect from ordinary chance. When they did the full statistical accounting, they concluded that the data did not warrant adding bubble collisions to our picture of the universe, and they set a firm upper limit, that there are fewer than about 1.5 detectable collision imprints across the entire sky, which is a careful scientist's way of saying, we looked hard and we don't see them. They also noted, pointing forward, that Planck's sharper data could test the idea more definitively still. The collision picture isn't ruled out in its gentlest forms, but there's no positive evidence for it, and in its boldest form, it slides toward being untestable, which in science is a kind of gentle exile. So let's gather the suspects and lay them out honestly, because the honest picture is the whole payoff. The confirmed giant void, weighed directly by the bending of light, is far too weak, good for 1/5 of the effect at most, and probably innocent of even that once the lensing is folded in. The cosmic texture, once the frontrunner, has quietly lost its statistical support and left no gravitational trace. Penrose's previous eon Hawking points were checked twice by independent teams, and each time the signal shrank back into ordinary chance. The bubble collision from a neighboring universe was actively hunted with a search built for exactly that, and came up with nothing above the noise. Every exotic answer, when tested, has failed to hold up. And the one conservative answer that everyone wanted has failed too, quantitatively, by a factor of 5 to 8. Which leaves the least dramatic possibility of all, the one that's easy to overlook precisely because it's so undramatic. Maybe nothing exotic made the cold spot. Maybe it's simply a rare roll of the dice. Here's what that means and why it's not a cop-out. The standard picture says the little temperature wobbles in the ancient light are random, scattered according to that calm bell curve statistics. But random doesn't mean uniform. Random means that occasionally, rarely, you get an outlier, a patch that happens to be much colder than typical, just by the ordinary luck of a genuinely random process. Flip enough coins and you'll eventually get 10 heads in a row. It doesn't mean the coin is haunted, it means you flipped a lot of coins. The cold spot might just be the 10 heads in a row of the young universe, an unusual but perfectly natural fluctuation baked in from the start, a primordial outlier that needs no new physics at all. And there's a real reason to take this seriously beyond it being the boring option. Remember that the void explanation failing actually points toward this. If the cooling isn't coming from something in front of the spot, along the line of sight, then it was more likely there from the very beginning, imprinted into the light at the moment the fog cleared. The lensing result, which killed the void, quietly strengthened the case that the cold spot is primordial. And the skeptics of new physics, people like Seshadri Nadatha and others, have long argued that a roughly 3 standard deviation feature just isn't that extraordinary, that a universe this large is entitled to a few unusual patches without anything strange going on. But now I have to introduce the idea that undercuts even the significance, the one that haunts this whole subject, because being honest about it is the most important thing in the story. It's called the look elsewhere effect. Here's the picture. Imagine you scan a whole sky full of clouds looking for one that resembles a face. You will find one. Not because faces are hiding in the sky, but because you looked at thousands of clouds, and with that many chances, some cloud somewhere is bound to line up into eyes and a mouth. Now, if a friend had pointed at one specific cloud in advance and said, "That one will look like a face," and it did, that would be remarkable. But finding a face cloud somewhere after scanning the whole sky is nearly guaranteed and means almost nothing. The cold spot was found by scanning the whole sky. Nobody predicted in advance that there would be an anomalous cold patch at that particular spot in Eridanus. It was discovered by looking everywhere for anything unusual and then noticing the most unusual thing, which means its apparent rarity, that under 1% figure, is inflated, maybe badly, because we gave ourselves the whole sky's worth of chances to find something odd. Correct for how many places we looked, and that impressive significance shrinks, possibly down to the point where it's not significant at all, just the most unusual patch you'd expect to find on any random sky if you went hunting for the most unusual patch. This is the strange part, and it's an honest strangeness, not a dread one. The very thing that makes the cold spot feel meaningful, that it's the coldest, biggest anomaly on the map, is partly an artifact of it being the thing we singled out for being the coldest, biggest anomaly on the map. We may be listening to static and hearing a tune. So is the cold spot significant at all? That is a live, honest, unresolved question, and the answer depends on subtleties that reasonable experts weigh differently. And here we arrive at the one test that everyone hoped would settle it, the test that could, in principle, tell a primordial cold spot apart from a line of sight one, cleanly. I mentioned earlier we'd come back to it. It's polarization. Here's the idea, and it's genuinely clever. Ancient light doesn't just have a temperature, it also has a faint polarization, a subtle orientation to its waves, imprinted at the moment the fog cleared by the way matter was moving and clumping right then. And crucially, a cold spot that was born primordial, printed into the light at the very beginning, should carry a matching polarization signature, a correlated ring of a particular pattern formed right there at that ancient wall. But a cold spot made later, by a void along the line of sight or by a texture's gravity, would be a purely gravitational effect that happened long after the light was already flying, and it would leave essentially no such polarization pattern. So the polarization is like a birth certificate. It could tell us, in principle, whether the cold spot was born with the universe or acquired its chill on the road. In principle. Here's the deflating, honest truth. The polarization signal we'd need to measure is extraordinarily faint, and the discriminating power of even our best instruments turns out to be weak. Forecasts made back around 2011 by Vielva and colleagues worked out how well various experiments could tell the two cases apart using this polarization test, and the numbers were sobering. An ideal, perfect experiment might reach useful discrimination, but for Planck, the actual instrument, the forecast power was small, and when the test was applied to real data from WMAP's 9-year maps, the result came back at around 32% significance, which is to say, inconclusive. Planck's own stacked polarization analyses of the region are consistent with the standard model, but hampered by noise, and no experiment to date has decisively detected or ruled out the predicted polarization ring. The birth certificate exists, in theory. We just can't read the handwriting yet. Why does this matter? Because it brings us face to face with the deepest limit in the whole subject, the honest edge. And it's not a limit of cleverness or funding, it's a limit built into our situation. We have only one sky. Sit with that, because it's the real answer for now, and it's a profound one. In most of science, when you want to know if something is a fluke, you repeat the experiment. Run it 1,000 times and the flukes wash out and the real effects stand up. But we cannot repeat the universe. There is one cosmic microwave background, one cold spot, one arrangement of the largest structures there are, and we are inside it, looking out, with no way to step outside and draw a second sky for comparison. Physicists call this cosmic variance, and at the largest scales it sets a hard ceiling on how sure we can ever be about any single grand feature. The cold spot is a sample size of 1. In a universe we get exactly 1 draw from, which means the honest edge, the thing this whole subject cannot settle, is this. We do not know whether that one cold patch is a rare but ordinary roll of the primordial dice, or the trace of something structural in the young universe that we don't yet understand. And with only one sky to measure, that question may stay genuinely open, not for lack of brilliance or better telescopes, but because you cannot beat cosmic variance with cleverness. Some questions in cosmology may simply stay underdetermined forever because we only ever get one look. This is not a failure, it's a fact about our position, honestly named. Where the science reaches its edge, the honest move is to point at the edge and stop, rather than fill the gap with a story we can't check. Now let me pull all the way back, because after all that testing and deflating, there's real understanding to gather up, and it's worth holding. Here's what we actually know, and it's a lot. The cosmic microwave background is real, the oldest light there is, released when the fog of the young universe cleared about 380,000 years after the beginning, now cooled to a faint 2.7 degrees above absolute zero and smooth across the whole sky to within 18 millionths of a degree. That smoothness is the standard model of cosmology being triumphantly right, and within that smoothness sits one genuine flaw, the cold spot, discovered in 2004 by Patricio Vielva, Marcos Cruz, and Enrique Martinez Gonzalez in Santander in WMAP's data, confirmed later by the European Space Agency's Planck satellite, a cold patch over 1 billion light-years across in the direction of Eridanus, wrapped in a faint warm ring, colder than the smooth story is comfortable with. It's real, that much is settled, and here's what we've learned by testing every door. The confirmed Eridanus supervoid, real and enormous, and mapped by the Dark Energy Survey on the Blanco telescope in Chile, explains at most 10 to 20% of the chill through the Integrated Sachs Wolfe effect, and the direct weighing of mass by gravitational lensing, in Owusu's Planck analysis, argues it explains even less. The cosmic texture faded when the statistics and the lensing gave it no support. Roger Penrose's conformal cyclic cosmology, with its Hawking points from a prior eon, made a testable prediction that independent teams, from Vehus and Ericsson through Zhao and Scott, checked and found consistent with ordinary chance, a signal that shrank from 99.98% to barely 1 standard deviation under honest reanalysis. And the bubble collision from a neighbouring universe, hunted deliberately by Stephen Feeney and Hiranya Piris at University College London, left no mark above the noise, fewer than 1.5 detectable collisions across the whole sky. Where does the evidence actually point, once you weigh it all? Toward the least dramatic reading. Most likely, the cold spot is a modest, genuine feature of the young universe, a rare primordial fluctuation with perhaps a small contribution from the void along the way, and its apparent significance may shrink further once you account for how much sky we scanned to find it. The exotic readings, the universe before ours, the collision with a neighbor, are not supported by the data. That's not a thrilling verdict, but it's an honest one, and there's a quiet dignity in the field arriving at it, in preferring the boring truth to the exciting story when the measurements demand it. And where does all this show up, out in the world you live in something more valuable than any single answer? The whole apparatus that let us find and test the cold spot, satellites chilled to 1/10 of a degree above absolute zero, telescopes in the Andes weighing invisible mass by the bending of light, algorithms built to search the entire sky for the fingerprints of other universes, is the same apparatus that pins down the age of the cosmos, maps the invisible scaffolding of dark matter, and tests whether our deepest ideas about gravity and the young universe hold together. The cold spot is one thread. Pulling on it tugs the whole tapestry, and the fact that the tapestry holds, mostly, is the real result. The standard picture survived every test we threw at it here, and where it strains, at this one cold patch, it strains honestly, in the open, in a way we can name. When I first sat with all of this, the thing I couldn't stop thinking about wasn't any single theory. It was the void. The way the most reasonable answer turned out to be true and still not enough. Present and still innocent. Real and still short by 80%. There's something in that I keep coming back to. Being right by only 20% and admitting it and going looking for the rest instead of pretending the 20% was the whole story. That's a kind of honesty I find genuinely moving, in the best way, and it's the opposite of how we usually tell stories about the universe. There's a detail about the discovery I skipped past, and it rewards a closer look, because it tells you something about how careful the Santander team had to be. When Patricio Villalba and Marcos Cruz first ran that specially shaped filter across the WMAP map, the thing they measured wasn't the coldness directly. It was a subtler statistic called kurtosis, which is a fancy word for a simple idea. Kurtosis measures whether a bunch of numbers has fatter tails than a plain bell curve, whether it produces more extreme outliers than pure randomness should. Picture the heights of people in a crowd. Mostly they cluster around average, and the very tall and very short are rare, tapering off smoothly. That's a normal spread. But if you found a crowd where the extremes were far more common than they should be, more giants and more very short people than the smooth curve predicts, you'd know something odd was going on, even before you spotted any single individual. That's what the filter caught first. Not the cold spot itself, but its statistical shadow, an excess of extreme values at a scale of about 4 degrees. Only when they chased that shadow to its source did the single cold patch in Eridanus fall out as the culprit. The anomaly announced itself as a whisper in the numbers before it ever showed its face. And I think that's worth pausing on, because it's how a lot of the deepest discoveries actually happen. Not with someone staring at a picture and gasping, but with a filter beeping over a statistic, a number coming out slightly wrong, a tail slightly too fat. The universe rarely shouts. It leaves a fingerprint on a measurement, and someone patient enough to be running the measurement notices the smudge. Now, one thing that can quietly mislead you in all of this is the word significance, and it's worth being precise because it's the hinge the whole debate swings on. When physicists say the cold spot is a 3 sigma feature or a 1% feature, they're speaking a specific language. Sigma is a measure of how far from ordinary something is, counted in units of the normal spread of random chance. 1 sigma is unremarkable, the kind of wobble you see constantly. 2 sigma starts to raise an eyebrow. 3 sigma, the neighborhood the cold spot lives in, means something that would happen by chance only about 1 time in a few hundred. It sounds impressive, and in a laboratory experiment you can repeat, 3 sigma is genuinely interesting, worth a second look. But here's the catch that keeps coming back to bite us. Those numbers assume you knew what you were looking for and where. They assume the friend pointed at the cloud in advance. The moment you're scanning the whole sky for anything unusual, the arithmetic of chance changes underneath you, and a 3 sigma find becomes far less surprising than it sounds. This is why the same feature can be described honestly as both anomalous and unremarkable by 2 careful scientists who simply weigh the look elsewhere correction differently. They're not disagreeing about the data, they're disagreeing about how impressed to be, and that turns out to be a genuinely hard question.
Let me ground the scale of this thing one more time, because the numbers are easy to say and hard to feel, and feeling them is the point. The cold spot spans about 10 degrees on the sky. Hold your fist out at arm's length and it covers about 10 degrees. So the whole anomaly is roughly a fist width of sky, which doesn't sound like much until you remember what's printed on that fist width. More than 1 billion light years of the young universe, laid across the inner wall of everything we can see. When you look toward Eridanus, a faint river of dim stars in the southern sky, you are looking, past all of them, past every star in our galaxy and every galaxy beyond, at a cold mark on the oldest light, a mark wider than the largest structures the cosmos knows how to assemble. And it has been sitting there, unchanged, since before the first star ignited anywhere. The light carrying its chill set out on its journey when the universe was 380,000 years old, and has been traveling toward us for over 13 billion years to deliver the news that one patch came out cold. Here's the strange part about that patience. Everything else in the sky has a history you can watch unfold. Stars are born, burn, and die. Galaxies collide and merge over billions of years. But the cold spot doesn't do anything. It was printed once, at the moment the fog cleared, and it has simply been in transit ever since, a frozen frame from the universe's infancy, arriving now. We're not watching a process. We're reading a message that was sealed before anything we call an object existed, and opened only when the light finally reached our instruments in the 21st century. There's a question I've been holding back, and it's the one a thoughtful person asks about halfway through all this. If the cold spot is so hard to explain, and if none of the answers work, why don't cosmologists just throw out the standard model? If the smooth story keeps failing at this one spot, maybe the smooth story is wrong. It's a fair challenge, and the answer is instructive. They don't throw it out because a model isn't judged by its single worst-fitting point. It's judged by the thousands of things it gets right. The standard picture, ΛCDM, predicts the overall pattern of those millionths of a degree wobbles across the whole sky with breathtaking accuracy. It predicts how galaxies are distributed, how the light was polarized, the abundance of the lightest elements forged in the first minutes, the very rate at which the universe expands. It passes test after test after test, and against all of that, you have one cold patch that sits at maybe 3 sigma, in a place we found by looking everywhere. A single anomaly, however striking, doesn't outweigh a mountain of confirmations. It becomes a footnote to investigate, not a reason to burn the textbook. The honest scientific posture is to hold both truths at once. The model is extraordinarily good, and it has a loose thread we haven't tied off. Both are true, neither cancels the other. And this is usually where the cold spot gets treated, as a footnote, a curiosity mentioned in passing and moved past. But look at it closely and it opens onto something larger, because it isn't actually alone. This is a thread worth pulling, because the cold spot turns out to be one member of a small, strange family. When cosmologists went hunting through that same ancient light for other departures from perfect smoothness, they found several, and they don't obviously fit together. There's a feature called the low quadrupole, where the largest scale variation in the sky is weaker than the standard picture predicts, as if the biggest ripples were somehow damped. There's a peculiar alignment, half-jokingly nicknamed the axis of evil, where certain large-scale patterns in the ancient light seem to line up with one another,
and even, uncomfortably, with the plane of our own solar system, when they ought to be randomly oriented. There's a hemispherical asymmetry, where one half of the sky seems to carry slightly more power in its fluctuations than the other, as if the universe had a faintly preferred side. And there's the cold spot. 4 oddities, each individually modest, each hovering in that same frustrating neighborhood of significance where you can't quite dismiss it and can't quite trust it. Now, here's the genuinely open question, and it's the kind that keeps people up at night in the good way. Are these 4 things unrelated coincidences, 4 separate rolls of the dice that each came up slightly odd? Or are they connected, 4 symptoms of a single underlying cause we haven't identified? Something about the young universe that the smooth story is missing. Nobody knows. If they're independent, then finding 4 mild anomalies across a whole sky is roughly what you'd expect from chance, and there's nothing to explain. But if they're linked, if there's one hidden mechanism tying the damped large scales and the strange alignments and the asymmetry and the cold patch together, then it would be a genuine clue about physics we don't yet have. And with only one sky, telling those 2 possibilities apart is monstrously hard, because you can't gather more skies to see whether the pattern repeats. It's the look elsewhere problem again, wearing a bigger coat. Scan enough properties of one universe, and a few will always look strange. The question of whether that strangeness means anything is exactly the question we may never be able to close. I find this the most quietly gripping part of the whole subject, more than any single exotic theory. Not the drama of a universe before ours, or a collision with a neighbor, but the sober possibility that our one and only cosmos carries a handful of faint irregularities that might be nothing or might be everything, and that we may be permanently unable to tell which. There's a humility in that which the flashier stories miss entirely.
Let me bring in one more real measurement, because it shows how ingenious people get when they're pinned against the wall of having only one sky and refuse to give up. Remember that the whole difficulty with reading the cold spot's birth certificate came down to the faintness of its polarization. But there's a specific version of that test worth naming because it's the sharpest tool anyone has proposed. It's called the temperature E-mode cross-correlation, and the idea is to look not at the temperature alone and not at the polarization alone, but at how the 2 dance together. A cold spot born at the ancient wall, primordial, should show a particular correlation between its temperature dip and the twist of its polarization, a coordinated pattern laid down together at the same moment. A cold spot acquired later, on the road, from a void's gravity, would show the temperature dip with essentially no matching polarization dance, because the polarization was already fixed long before the light ever met the void. So the correlation between the 2 is the cleanest possible discriminator. It's like being able to tell a photograph taken at the scene from one taken later and edited in, by checking whether the lighting on the subject matches the lighting in the room. The trouble again is that the signal is desperately faint, and the forecasts made by Wolfe and his colleagues around 2011 were honest about it. Even a nearly ideal experiment could barely reach the sensitivity needed. For Planck, the best instrument actually flying, the discriminating power was small, and when a later team applied the method to real WMAP data, the result landed at around 32%, comfortably in the territory of "we cannot tell." There are future ground-based experiments, like the one called Quixote, that might do marginally better, but even the forecasts for those are humbling. The birth certificate is written in ink too pale to read with the eyes we have, and possibly with any eyes we'll build, because the fundamental limit isn't the instrument. It's that the signal itself is intrinsically weak, and we have one copy of it. That phrase keeps returning, and it should, because it's the honest heart of everything. One copy, one sky. There is a temptation, whenever science hits a wall like this, to feel cheated, as though a definite answer is owed to us and is merely being withheld by insufficient effort. But that's not the situation here. The situation is more interesting and, in a way, more dignified.
We have run into a limit that isn't about us at all. It's about the object we're studying. A universe, being the whole of everything, comes in a quantity of exactly 1, and you cannot do statistics on a sample of 1 the way you can on a sample of thousands. The uncertainty isn't ignorance we can cure. It's a feature of what it means to study the largest thing there is from the inside.
Andras Kovac, who led the careful mapping of the Eridanus supervoid with the dark energy survey, put the whole predicament in a single sentence that I think is the wisest thing anyone said in this entire story. Having the coincidence of these two individually rare structures, he said, the rare void in the cosmic web and the rare cold patch in the ancient light, is basically not enough to prove causality with the scientific standard. Sit with what that means. Here is a man who found the void, confirmed it, weighed it, and who would have every human incentive to declare that he'd solved the cold spot. And instead he says, plainly, that two rare things sitting in the same direction is not proof that one caused the other. Because rare things can line up by accident, and the whole discipline of science is the refusal to mistake a coincidence for a cause without earning it. That restraint, from the person best positioned to overclaim, is science at its finest, and it's a quieter kind of impressive than any headline about other universes. Think about how easy the alternative would have been. The void is real, the cold spot is real, they're in the same direction. The temptation to draw a line between them and call it done is enormous, and it would have made a cleaner story. But the lensing said no, the arithmetic said no, and the control fields, those ordinary patches of sky with similar voids and no cold spots, said no. And the people who most wanted a tidy answer were the ones who reported, honestly, that they didn't have one. There's a version of courage in that which doesn't get celebrated enough. The courage to publish the result that leaves the mystery open rather than the one that closes it prettily. The same restraint runs through the exotic end of the story too, and it's why the Penrose episode is ultimately not a story about one man being wrong. Roger Penrose has been right about profound things before. His singularity work, the reasoning that earned the Nobel Prize, was itself a bold leap that turned out to describe reality. So when a mind of that caliber says the marks of a universe before ours might be printed on our sky, you don't laugh. You check. And the checking, by Ingun Vehus and Hans Christian Eriksen, by Dylan Zhao and Douglas Scott, by teams running the numbers through simulations and machine learning, is not an attack on him. It's the highest respect the community can pay an idea, taking it seriously enough to test it to destruction. The signal didn't survive. 99.98% became 87%, became, honestly, nothing you could hang a discovery on. And that outcome, a beautiful idea failing a fair test, is not a tragedy. It's the process working exactly as it should, on its most distinguished participants, exactly as it would on anyone. I keep coming back to a small human image from all this that I can't shake. A graduate student, Stephen Feeney, at University College London, sitting down to write a computer program whose whole job was to search the oldest light in the universe for the bruises left by collisions with other universes. Not as a thought experiment, as a real search with real data that could have come back yes. And when it came back no, fewer than 1.5 detectable collisions across the whole sky, that no was itself a genuine result, a real boundary drawn around what our universe will let us see. Hiranya Piris said the thing that pricked her curiosity was the sheer difficulty of searching every possible size of imprint at every possible place in the sky. That's the tone of this whole field at its best. Not fear of what's out there, not hunger for a sensational answer, but curiosity strong enough to build the tool and honesty strong enough to report whatever the tool finds, including nothing. So what does the sky actually let us conclude, standing here with every door tested? That the cold spot is real, and that its cause is, most probably, the least exotic thing on the menu.
a rare but natural fluctuation from the universe's earliest moment, printed into the ancient light, and now perhaps looking a little more anomalous than it really is, because we found it by hunting for the most anomalous thing on the map. The giant Eridanus supervoid contributes a little, but was weighed by the bending of light and found far too slight to be the answer. The cosmic texture faded for lack of support. The hawking points of a prior eon and the bruise of a colliding neighbour were searched for, deliberately and repeatedly, and did not appear above the ordinary noise of a single random sky. The dramatic readings do not survive contact with the measurements. The plane one mostly does, and even the plane one carries an asterisk we can't erase, because with one sky we can never fully separate a real, rare feature from an artifact of having looked everywhere. So where does that leave us? With something better than an answer, I think, though it takes a certain temperament to see it that way. It leaves us with a genuine, honest, still open question, held in exactly the right amount of light. Here is what we understand now that we didn't at the start. The cosmic microwave background is the oldest light there is, the flash of the young universe going transparent about 380,000 years after the beginning, cooled and stretched over billions of years into a faint microwave glow, smooth across the whole sky to within 18 millionths of a degree. A smoothness that stands as one of the great triumphs of the standard model of cosmology. And on that smooth face sits one real flaw, the cold spot, found in Santander in 2004 by Patricio Vielva, Marcos Cruz, and Enrique Martinez Gonzalez in the WMAP data. Confirmed by the European Space Agency's Planck satellite, a cold patch over 1 billion light-years wide toward the constellation Eridanus, wrapped in a faint, warm ring, colder than the smooth story would predict. We understand that the confirmed Eridanus supervoid, mapped by the Dark Energy Survey on the Blanco telescope in Chile, explains at most a fifth of the chill through the Integrated Sachs Wolfe effect, and probably less once gravitational lensing weighs the mass directly. And we understand that the boldest explanations, Roger Penrose's conformal cyclic cosmology with its hawking points from an eon before ours, and the bubble collision with a neighbouring universe hunted by Stephen Feeney and Hiranya Piris, were tested against ordinary chance and did not hold up. Where does it show up in your world? In the extraordinary machinery of looking itself. The satellites cooled to a breath above absolute zero. The telescopes in the Andes weighing invisible matter by the bending of starlight. The algorithms combing the entire sky for the faintest circular scar are the same instruments and the same methods that measure the age of the cosmos, chart the hidden scaffolding of dark matter, and keep testing whether our deepest picture of the universe holds together. The cold spot is one thread in that fabric, and the fact that pulling on it leaves the fabric mostly intact is itself the quiet reassurance underneath all the drama. The standard picture survived. Where it strains at this one cold patch, it strains in the open, honestly, in a way we can point to and name. And here is the honest edge, the one thing this whole subject cannot settle, stated plainly because plainness is the only decent way to state it. We do not know whether that one cold patch is a rare, ordinary roll of the primordial dice, or the faint trace of some structure in the young universe we haven't yet understood. And with only one sky to measure, no way to run the experiment twice, no second cosmos to compare against, that question may stay open no matter how fine our instruments become. Not because we aren't clever enough, because we get exactly one look, and some questions asked of the whole of everything are simply underdetermined by a single glance. That's not a defeat, it's an honest description of where the knowing stops. If you like understanding things this way, sitting with a real mystery long enough to see both what we've learned and where the edge honestly is, subscribe and we'll figure out the next one together. The oldest light in the universe has traveled 13 billion years to reach us, and it arrives almost perfectly smooth, carrying one cold mark we still cannot read. One sky, one cold patch, and a question older than the stars, still waiting, still open, still there. There's one more piece of this worth holding, and it comes from the way the Planck team itself described the whole family of anomalies, because their own words capture the careful posture better than any summary could. They noted that the absence of any matching features in the polarization might mean that these temperature oddities, if they are not simply flukes, could be the work of some later effect, something that happened to the light on its long journey rather than at its birth, whether a void's gravity or a texture or something else along the way. Notice the shape of that sentence. If they are not simply flukes. Might, could. This is the language of people standing precisely at the edge of what the measurement allows, refusing to step past it in either direction. They will not declare the cold spot meaningful, and they will not declare it meaningless. They name exactly what the data supports and stop there. And that discipline, that willingness to leave a sentence unfinished because the universe hasn't finished it for us, is the whole ethic of the thing in miniature. Think about what it takes to leave a question that open, that publicly, for that long. 2 decades now since Patricio Villalva's filter first beeped over that fat-tailed statistic in Santander, and the honest answer is still, we don't know for certain, and we may not be able to. Most fields cannot tolerate that. Most stories can't end that way. But the oldest light doesn't owe us a tidy ending, and the people who study it have learned to make peace with a mystery that might never close. Not by pretending it's solved, and not by inflating it into something it isn't, but by holding it at exactly its true weight. Real, modest, unexplained, and possibly unexplainable, all at once. So where does that leave us? With a cold patch on the oldest light there is, and a handful of tested, honest answers, none of which quite finishes the job. The cosmic microwave background, that faint glow from 380,000 years after the beginning, smoothed to 18 millionths of a degree across the whole sky, carries in the direction of Eridanus one real flaw. Found by Patricio Villalva, Marcos Cruz, and Enrique Martinez Gonzalez in the WMAP data, confirmed by the Planck satellite, more than 1 billion light-years wide. The confirmed Eridanus supervoid, weighed by the Dark Energy Survey and by gravitational lensing, explains at most 1/5 of it. Roger Penrose's picture of a universe before ours, and the search for a collision with a neighboring one, were tested against ordinary chance and did not survive. The most likely answer is the plainest, a rare fluctuation from the young universe, perhaps looking stranger than it is because we found it by hunting for the strangest thing on the map. And where it shows up is in the machinery of looking itself. The chilled satellites and the mountaintop telescopes, and the algorithms that comb the whole sky. The same tools that measure the age of everything and map the dark scaffolding underneath it. The honest edge is this. We do not know whether that one cold mark is an ordinary rare accident or the trace of something we haven't understood. And with only one sky to measure, that question may stay open forever. Not for want of cleverness, but because we get one look and no more. If you like understanding things this way, staying with a real mystery long enough to see both what we know and where the knowing stops, subscribe and we'll figure out the next one together. The oldest light in the universe has been traveling toward us since before the first star, and it arrives carrying one cold mark we still cannot read. One sky, one cold patch, and a question older than the stars.